Section 5.5 deals with intermolecular forces. The first thing we need to talk about in this lesson is the difference between intramolecular forces and intermolecular forces. Intra means within, so these are the forces within the molecules. They are the bonds we have talked about: ionic, metallic, and covalent. As seen in this picture, you can see that there is a covalent bond, in particular a polar covalent bond, between the hydrogen and the chlorine. This would be considered an intramolecular force. Breaking intramolecular forces requires a tremendous amount of energy. The stronger the bond, the more energy needed to break it. Remember, when you are breaking bonds, you are going through a chemical change. A chemical change is one where the substances will become something different after the change. So bonds are broken and rearranged to form new molecules. Inter means between. So these are going to be the forces that are between the molecules of a covalent compound. If we take a look at the picture, you will see that there is a dotted line between the two hydrogen chloride molecules. That dotted line represents the intermolecular force. It is holding the two molecules closely together. Breaking intermolecular forces does not require as much energy to break compared to an intramolecular force. And that is because you are just separating the molecules from each other. You are not breaking bonds. Examples of this would be breaking glass or boiling water, and these are all examples of physical changes. The substance that you originally start with will be the same substance in the end. It's just going to have a different form. The first type of force that we will discuss are called London dispersion forces, sometimes just called dispersion forces, and it's abbreviated as LDF. They are the primary force between nonpolar molecules, but they are found in all molecules. So let's discuss what makes a London dispersion force. The first thing we want to remember is that all molecules have electrons, and these electrons are moving around the nucleus in spontaneous movements. If the electrons move to one side and they momentarily gang up so that there's more on one side than the other, that lopsidedness creates a partial negative charge in one area and a partial positive charge in another area. This then creates a temporary dipole, also known as an instantaneous dipole. If you take a look at the diagram down at the bottom on the left-hand side, you can see that all the electrons are kind of evenly dispersed. But remember, these electrons are moving. So if they gang up on one side, like you see in the picture on the right-hand side, we will get a instantaneous temporary negative charge on one end of the molecule and a temporary positive end on the other. And that makes that have a dipole. It's just temporary. It will change within nanoseconds because of the continual movement of the electrons in various places in the atom. So in a nonpolar molecule, once the electrons have ganged up on one side, they create this temporary dipole of partial positive and negative ends. That means that the molecule is temporarily polar. That will induce a dipole in another nonpolar molecule, shifting the electrons so that one end becomes temporarily partially negative and the other side partially positive. It is then the attraction between the positive and the negative end, and remember these are temporary, that is going to create the London dispersion force. London dispersion forces are weak forces holding two nonpolar molecules together. Here's another diagram where we see the helium atoms with their two electrons out in the cloud, and as soon as we see the second helium atom's electrons shift over to the left, that's going to make this partially negative, partially positive, and that's going to induce a dipole, and we end up seeing this relationship over here, and that is the London dispersion force. London dispersion forces are the weakest of all the intermolecular forces because the molecules can't form the dipoles permanently. It is only a temporary dipole. Another important fact of London dispersion forces is that the larger nonpolar molecules will have stronger London dispersion forces. And that's because there will be more electrons moving around creating that temporary dipole. There's usually strength in numbers. So the more electrons that an atom has, and that's correlated to the mass of the atom, the more movements it can have and the greater the partial negative and positive charge will be. So that concept explains why these three elements that are found in the halogen family, group 7A, have different physical states. Remember that chlorine is Cl2, bromine is Br2, and iodine is I2. They are all nonpolar molecules, and so there are London dispersion forces between their molecules. But because iodine has 106 electrons versus the 34 that chlorine does, there's going to be a stronger set of forces holding iodine together, and the stronger the forces, the closer the atoms get, and then that becomes a solid, whereas the weaker forces are going to give you the gaseous form. Of course, bromine is intermediate in the number of electrons, so it has intermediate forces, and that's why it's at a liquid state. So the greater number of electrons, the stronger the forces.
Dipole-dipole forces are the primary force between polar molecules. Polar molecules already have permanent dipoles. They have permanent partial positive and partial negative charges on their atoms due to the electronegativity difference of them. So, the positive area of one polar molecule can attract the negative area of another to get the dipole-dipole force to bring the particles closer together. In general, dipole-dipole forces are stronger than London dispersion forces because those dipole-dipole forces are permanent, whereas the London dispersion forces are instantaneous or temporary. Notice in the diagram below that the partially negative end of one molecule is attracted to the partially positive end of another molecule, creating that dipole-dipole force. It is an intermolecular force pulling the molecules closer together and holding them in either a liquid or solid state. In the last couple of diagrams, we've only looked at two molecules and the forces between those two molecules, so I wanted you to get a better idea of what the forces would look like of attraction and repulsion if there were more than two molecules. The last type of intermolecular force is called hydrogen bonding, and it's a little misleading because it's not a bond. It is actually one of the strongest forces out there, and it is actually a dipole-dipole force. It only occurs between the hydrogen atom of one molecule and a fluorine oxygen or nitrogen of another molecule. This very strong dipole-dipole force forms because fluorine, oxygen, and nitrogen are all extremely small, as well as hydrogen, and they're very electronegative atoms, meaning that they have a tendency to pull hydrogen's electron very, very close to themselves. In the diagram to the left, you can see that there is a hydrogen bond between the hydrogen atom of one ammonia molecule and the nitrogen's lone pair of a different molecule. You can also see on the diagram to the right that there are hydrogen bonds in water. And in fact, each water molecule can allow two hydrogen bonds to form to other water molecules. And that's one of the reasons why water is so unique. Because of its hydrogen bonds, it's going to have extremely high boiling points, it's going to have high surface tension, it's going to have low vapor pressure, and so forth. The hydrogen bond is the strongest of all the intermolecular forces. Remember that hydrogen has no inner electrons to counteract the proton's charge. It's an extreme example of polar bonding, with the hydrogen having a very large positive charge. And this very large positive charge is highly attracted to those lone pair of electrons on F, O, or N. Hydrogen bonds attach the base pairs of adenine and thymine, guanine and cytosine in our DNA molecule. So this type of intermolecular force is extremely important in biology.
Let's rank the forces of attraction in order from weakest to strongest. Remember that the intramolecular forces are the bonds of ionic, covalent, and metallic. And in a previous discussion, we have focused on the fact that the covalent bond is going to be the weakest, Then the metallic bond will be the next strongest, with the ionic bond having the strongest forces of attraction. In the next example, we're going to rank the intermolecular forces. These are the forces between the molecules. Remember that the London dispersion forces are the weakest forces. They are found in all molecules, but they are the primary force between nonpolar molecules. Temporary dipoles, thus the weakest of the forces. We then have our permanent dipoles that will hold our polar molecules together, and that is our dipole-dipole forces. They are of greater strength in general. And then lastly, we have hydrogen bonding. Hydrogen bonding is the strongest type of dipole-dipole force, and it only occurs with a hydrogen attaching to or connecting to a fluorine, oxygen, or nitrogen of a different molecule. Lastly, we want to rank all the forces, intra and inter combined. We want to remember that the inter forces will always be the weakest. So we're going to say London dispersion, dipole-dipole, hydrogen bonding, and then we hit the bonds which require more energy to break. And that will then be the covalent bond, the metallic bond, and the ionic bond. Now there is one other force that we need to talk about, and that's a special force called the network covalent bond. And we'll talk about that in the next slide. But that would actually have greater strength than an ionic bond. Network covalent bonds are what hold the carbon atoms together in the allotropes of diamond and graphite. An allotrope simply means form. So we have actually three different forms of carbon. We've got diamond, which shows the carbon atoms in a tetrahedral arrangement. It's a very strong, very strong arrangement, which creates a very hard substance. Diamond has one of the highest melting points out there because of these very strong network covalent bonds. And then it's also found in the form of graphite. Now graphite's a little different because it is basically sheets of hexagonal carbon rings, and those are relatively strong. That's where the network covalent bonds are going to be hanging out. However, we have these very weak forces holding these sheets together. And just a little bit of force on those sheets can break those forces. And when they break the forces, then they can separate. And that's why graphite is very soft. In fact, your pencil is made up of graphite. So as you press your pencil lead onto paper, basically the carbon atoms are lining out on your paper because of that pressure. So network covalent bonds are special. They're only in certain compounds, such as silicon dioxide, which is quartz, and the different allotropes of diamond, graphite, and Buckminster fullerene. They have super strong bonding patterns, which means super high melting points.